here we have the interval of points from 0 to 1, just on the number line or on the x-axis. And here we have the unit square, which is all the points from 0, 0 to 1, 1 in the xy plane. So intuitively, it would seem that this is, in some senses, a bigger space. Maybe that it has more points or something. Because this is just a one-dimensional thing. It has a single line of numbers. But this one is like two-dimensional, and this fully fits inside here, like just a single line at the bottom, and then there's infinitely many copies, uncountably infinitely many copies of this number line inside this square. So it would seem that it's impossible to make a function that maps from here to here and hits every single point in the square. But that's actually not true. There's a way to make a space-filling curve that maps from here to here and hits every point. So to show you how this curve works, first we're going to describe an operation on paths. So take this triangular path that goes, so if we divide the square into 4 subsquares, take the triangular path that goes like this and goes through the midpoint. Then perform an operation on this path where you basically replace each of these with a mini copy of the triangle. So what that means is your next path is going to look something like this. Like this. And then, so you can repeatedly apply this operation. Each time, you turn each of these triangles into a little squiggly thingy. So the next path, I'm not going to draw all of it for the sake of time, but here's a quick visualization of some of the later functions in the sequence. As you can see, they get pretty dense pretty quickly. It would look something like this, and then this would repeat itself 4 times in each of the squares. So there's a couple important things to note about this operation. First thing is that the endpoints are preserved. So every single path starts at this bottom left corner and ends at this bottom right corner. Just even after you perform the operation, right? So this starts here, ends here, starts here, ends here. Another thing to note is that, so if we call this F1, we call this F2, we call this F3. Fn is going to be a path made up of 4 to the n little triangular paths, because each time you perform this operation, the number of triangular bits gets multiplied by 4. So here we have a single triangle bit, here we have 1, 2, 3, 4 little triangles. So Fn is going to have 4 to the n triangular segments, and each of those triangular segments is going to lie in a square that the side length is 1 over 2 to the n. So to see why, recall, so this square has side length 1. So to start with, this triangle lies in a square of side length 1. Then each of these triangles now lies in a square of half the length, right? So this has 1/2, 1/2. Sorry, we're going to call this F0 just to prevent off by 1 errors. The next thing that we want to prove is that this function is continuous, which intuitively just means that that basically there's no like holes in the function, right? So most functions that you can like draw without lifting your chalk from the blackboard are continuous, right? But if there's like a hole or a jump or something, then that would be discontinuous. So one other thing that we have to talk about is a metric. So in general, a metric generalizes the notion of distance, right? So you can have 2 objects, and you can define some kind of distance on them, which we call a metric. And if you define a nice enough metric that has some nice properties that you would expect a distance to have, then you can get some useful things that you can do with that metric. So we're going to define a distance between 2 functions. So if you take 2 functions, we're going to define the supremum metric as the maximum distance between those 2 functions at any point. So recall, with our functions over here, these are functions that basically map the unit interval into a subset of the unit square, right? So the first function, f0, is going to map this unit interval to, wait, no, this should be f1. Nope, this is So it maps this unit interval into this triangle, basically. F2 maps this unit interval, like stretches out and whatever, bends it, and maps it into this function. So if you look at, let's look at what the supremum metric is between any two functions, right? And so we actually don't care about this, what it is exactly, but we need a kind of general idea of whether the distance between functions goes down as the functions get, or the indices get higher. So let's take a look at this function, for example. So we split up the unit square into four. Oh, and one more modification we're going to do to what you would think of as distance is we're going to actually use the square distance instead of the traditional Pythagorean distance. So if you have any 2 points on the xy plane, the normal way you'd calculate the distance is you would like draw a line between them, do like the Pythagorean theorem to find the distance of the hypotenuse. We actually don't really need that. We only care about the maximum of either the horizontal or the vertical distance. Okay, so back to here. So between these two functions, what's the maximum distance? So this function is inside every single one of these squares. And the maximum distance between any 2 points in one of these squares, since the squares have side length 1 over 2 to the 2, which is 1 over 4. Nope. Sorry, 1 over 2 to the 1, which is 1/2. So like, say this point and this point. Since we only care about the maximum between the horizontal or vertical distance, this is going to be less than 1/2. So we can say, and so this function also goes in this square through various points. But any point on this function is going to be inside one of these smaller squares. And this function is also going to be inside each of those smaller squares, which means that the maximum distance has to be less than 1/2. If we do the same argument here, this function is going to go inside each of these smaller squares with side length 1/4. So any point on this function is going to go through one of these squares, say it's here. So say this function say we're looking at this point, right? This point is going to be in this small square. This F3 is also going to be inside this small square. So again, the maximum possible distance is 1/4. Turns out, as we keep going, this distance keeps getting smaller, right? So any two adjacent functions, the maximum distance is going to be 1 over 2 to the n. 1 over 2 to the n gets arbitrarily small. So there's another useful result that we're going to use, which basically says that any sequence that gets where the terms get arbitrarily close to each other is called a Cauchy sequence. C-A-U-C-H-Y. So, and so we can define basically the space of continuous functions, and then say that this is a Cauchy sequence of functions. And if that space is nice enough, which in this case it is, that means that sequence converges to something. So this sequence of functions converges to one final function, I guess, and we can call that function f. And f is continuous.
So how do we know that f hits all the points in the square?
So that's a really good question. So to prove this, that we're going to need a couple more tools, including the idea of closed sets and compact sets. So first, closed sets are sets that contain all their limit points. A limit point is basically a point where the set gets really close to it, but it doesn't necessarily hit it, although it can hit it. So if you look at, for example, the open interval 0, 1, so that's all the points between 0 and 1, but not including 0 and 1. Points are going to get really, really close, arbitrarily close to 1. They're never actually going to hit 1. That means 1 is a limit point. So that means this open interval is not closed. But if we include 0 and 1, then it becomes closed. It also becomes compact, which is another idea that's a little bit harder to define super neatly, but basically it means it's in some sense finite. Another nice theorem that says sufficiently nice functions from compact sets, the output is also a compact set. And we also know that compact sets are closed. So we know that f is nice, that's what we were proving earlier, or part of what it. And we know f is a function from this compact set into this square, which is also compact. So we know that the output of f is closed, which means it contains all its limit points. So if we can show that any point inside this square is a limit point of f, we can show, or of the output of f, we can show that that point is also inside the output of f directly because closed sets contain their limit points. Okay, so to do that, basically what we're going to do, so pick some arbitrary point in this square. We want to show that this is a limit point of f, and to do that, we basically want to show that, or a limit point of the output of f, and we want to show that points in the output of f get as close as we want to this point. So to do that, we're basically, first, notice that since this sequence of functions converges to f, that means that this sequence of functions gets as close as we want to f. So we can find the distance between fn and f, and then by just making f really big, we can make this as small as we want. The next thing is, again, note this like square argument. So for every fn, fn is going to hit each of these small squares with side length 1 over 2 to the n. So fn, so this point is inside one of the small squares. So fn is going to go at least within 1 over 2 to the n of this point. So the other thing is we can show the distance between some fn and the point that we want, we'll call it x, is at most 1 over 2 to the n. And so remember, so 1 over 2 to the n, we can just make that as small as we want by making n really big. And this we can also make as small as we want because that's basically the definition of convergence. So, and it's also true in general, because it's true in the real world and it's one of the important properties of a distance, is that the distance from x to fn, or the distance between x and f, has to be less than or equal to the distance between x and fn, and then fn to f. So basically you can think of this as like x is your point here, f is another point here, fn is a point here. If you go along this path, that can't be less than going straight from x to f. So if we just add these two together, we can see that the distance between fn and f plus the distance between fn and x has to be greater than or equal to the distance between x and f. And so since this can be as small as we want, this can also be as small as we want. So that means that x, which is just a random point in the square that we picked arbitrarily, gets as close as we want to f. That means that x is a limit point of f. Since f contains all its limit points, that means that x is hit by some point in f. So that completes our proof and shows that f is a function that's continuous, and it goes from this line to this square and hits every point.